Hi and welcome. I'm trying to learn electrical engineering, and after we've done what we're going to do, shoulder impingement training, and if you participate in the shoulder impingement training, then it's at your own risk. Now this is part 2, we were already over page in, so I'm going to read it now shortly. Potential difference. When a current flows in any conductor, a potential difference exists between the ends of a conductor. So there's something else inside of the conductor. This potential difference is measured in volts, usually by placing a voltmeter across the ends of a wire. So we're measuring before and after it has flown through the conductor, and we now in volt how much potential difference there was lost of our current of the electricity. Neither the current nor the potential difference will exist unless somewhere in the circuit concerned is a source of electrical energy. There is no current or electricity inside of a cable, circuit, or whatever, if there's not someone generating that electricity. This will usually be either a generator doing the electricity, which converts mechanical energy, or a cell which has a store of chemical energy. That is what we're meaning with a cell storing chemical energy, we're meaning a battery. The source of electrical, so we're saying either dynamo or battery, is doing the electrical current. This source of electrical energy is said to have an electromotive force, measured in volts, which is the total driving force available to push a current through each component in the circuit. I think the meaning the generator of the battery are doing a push of an electromotive force of 10 volt is the example, and now the electromotive force is 10 volt of its battery. It is often difficult to know when to refer to a potential difference and when to refer to an electromotive force. Both are measured in volts. I don't know why it is difficult to refer to them. Consideration of a simple circuit may make the distinction clear. Okay, we're talking about that. The potential difference across the ends of each of the resistors, A, B, and C, can be measured by placing a voltmeter across the ends of each in turn. So by measuring after the first resistor A, B, and C how much was lost at current. The total potential difference across the 3 resistors will be 9 volts. The first one absorbs 3, the second resistor takes 2 volts, and we have the other one 4. Together 4, 2, and 3 are 9 volts. 9 volts are now taken away by these 3 resistors. And this in fact will be the reading of voltmeter when it is placed across the terminals of the battery X and Y. I don't really get that part. We're saying the battery is one. Whatever, we're somewhere battery we're measuring A and B, X and Y. If now the switch is opened, the voltmeter across X and Y will read 10 volts. Somehow we are 10 volts. This reading informs us that the electromotive force of a cell is 10 volts. I think that's here on the side. The A is 10 volts, and down there 9 volts are absorbed, and here top 10 volts are the electromotive force, which is what the battery has. So this reading informs us that the electromotive force of a cell is 10 volts, the battery of a cell. Its total available voltage, the battery has 10 volts. When this electromotive force is applied to the circuit, the electromotive force causes the potential difference to be set up across each resistor in the circuit. And these potential differences total 9 volts. So the battery is pushing with 10 volts, the first resistor absorbs 2, the second 3, and the other one 4, and 9 volts are now in total absorbed, and there's just 1 volt left. Is that what resistors are for? I just realized that. This is for. So we're having 2 batteries with too much power, and now if you just want to have your little lamp burning, there has to be a resistor in the middle, and your lamp gets 50,000 volts for a whole city. It's like the whole thing of resistors. You will realize that 1 volt seems to be lost when the electromagnetic force of the battery is employed to drive a current around the circuit. This lost volt is the part of the electromagnetic force which is required to overcome the internal resistance of the battery itself as the current flows through it. Let's read it again. So you will realize that 1 volt seems to be lost. Yes, 1 volt is missing, but from your totally logic, there are 10 volts coming out, so there are just 9 missing. Whatever, for some reason 1 volt is lost. It doesn't really matter now, for example. Now 1 volt is lost, and that is required to overcome the internal resistance of the battery itself as the current flows through it. So when through the battery current flows, the battery itself will take 1 volt. It makes more or less sense. A final point of interest is that it is no more true to say a current flows in a conductor than a potential difference exists across its ends than it is to say that when a potential difference exists, a current must flow. Let's read it again, I think it's pretty easy. A final point of interest is that it is no more true to say a current flows in a conductor when a potential difference exists across its end. That is not true. When it is to say that when a potential difference exists, a current must flow. I don't know what I want to say, but I think it's pretty logical. So if you have an example the next time without such a complex sentence, we will understand it. I think the meaning, just because there is a potential difference, it doesn't mean there's a current flow. Whatever, I think it's pretty obvious in the next example you will get it. Both must exist together. Explaining it again. Both must exist together. Both a potential difference and the current, and neither can be considered as causing the other. Okay, the current is not causing the potential difference. There has to be a resistor or something in the middle. And both must exist together, the current and the potential difference. Yes. If there's no current or no electricity at all, there is no potential difference. If a river is dry, there is no difference in the water volume, which is even the word for it, which is flowing in. What is it? Whatever. Which is flowing in the water, there's no difference if there's no water at all. The electromotive force, on the other hand, is the cause of a variation, potential difference, of a various potential difference, and currents in the circuit because of the electromotive force is associated with a generator or cell which is a source of energy. Okay, yes, we got the last part. The electromotive force is associated with a generator because the generator is making the electricity, this current, and now this is pushing out what comes out. Okay, we get that. The electromotive force comes from the battery, from a cell of generator. And it is the cause of the various potential differences and currents in the circuit. It is at least, I get it so far, it's at least the overall big cause. If not the generator were to do electricity or current, there wouldn't be any at all, no potential difference. Now, don't know if I'm saying that is the cause why there is a potential difference. Whatever, that is at least necessary so that it's possible, there has to be electricity in the first place. It's just the terms potential difference and currents are names given to certain aspects of a situation in which electrical energy is being converted to other forms of energy, such as heat and motion. Let's read it again. So these both terms, potential difference and current, are names given to certain aspects of a situation. And in that situation, electrical energy is being converted to other forms of energy, such as heat and motion. And why does converting into heat or motion, making a potential difference, does it not just use it up? Or do they say that it's used up, that is the same as a resistor? I think it's pretty obvious whatever we're trying to explain, it's logical and understandable. The volt. They said that this is the thing in which it is measured. So volume of water is measured in a liter and mass of something is measured in whatever, I think it's in kilogram or something else. And volt is used for the power of a current. What are we doing here? We are doing short and midterm training over time already. In the previous volume, it was explained that work is measured in joules. In the previous volume, there's something written about physics unit 2. I don't have unit 1. In the previous volume, it was explained that work is measured in joules. That makes sense. Whatever I think it is. A joule is the work done when a force of 1 Newton moves in point of application through a distance of 1 meter. Let's read it again. I think it's not that hard. A joule is the work done when a force of 1 Newton moves its point of application for a distance of 1 meter. Okay, if there's electricity and it comes out at the other end of 1 meter, the amount of that is done, that is 1 joule. Moving 1 electricity to 1 electricity with 1 joule. I think that's the basic of it. I don't know if I understand it completely. That's the basic how it works. Do I understand here from that now? When work is done at the rate of 1 joule per second, this is said to be the power of 1 watt. So 1 joule, we're going to say 1 electron, 1 electron was brought to 1 meter at the end of the cable, that was 1 work, and it's the same as 1 joule. 1 watt, whatever, it's not all three the same. I think we're having the basics of it. A volt is defined as a potential difference which exists between 2 points when a column of charge passing between these points does 1 joule of work. Now we're talking about it. That was stupid. So a volt is defined as a potential difference which exists between 2 points when a column of charges passed between those points does 1. Now column is another type of electrical measuring. Now we're sending one electron to the other, electrons from one side, electricity from one side to the other one, and the amount which is lost is a potential difference, and the amount of the volt is lost if one column of amount of energy is shifted over. What is then lost after 1 meter is 1 joule of the. I think that is the broad framework, but I don't know what we know exactly mean. Because 1 joule per second is a watt, and also 1 coulomb per second is an ampere, we can reword the above statement as follows. Okay, we're saying now we can somehow calculate. Joule is the same as watt, and 1 coulomb is the same as an ampere, and 1 joule in 1 second is the same as an ampere. Whatever, it's just calculating around between gram and kilogram and tons, and when measured also per watt it is, per second, per hour, or per day. And I think it's just the same as all the other measurements, just with the bringing 2 or 3 together. It's a bit more complex, but it seems to be just the same system. A volt is defined as a potential difference which exists between 2 points when a current of 1 ampere does work at the rate of 1 watt. Whatever, we're bringing 1 ampere of electricity over to the other side, and we're doing that with 1 watt. That means with a power of 50 kilometers, whatever. We're bringing it over with that power, and that is now what is lost in that 1 meter is 1 volt. I think it makes more or less sense. So we're driving with a car over 1 meter over, and we're needing to drive it sounds so much of benzene, or of whatever a car now needs. Gasoline. We're needing sounds so much gasoline to drive over, and what it has caused it gasoline to drive that 1 ton of car over to the other side in 1 second is the amount of volt. So the car weighs 1 ton, that is ampere, to bring 1 ampere, 1 ton of car over to the other side of 1 meter distance in a time of 1 second. So the ampere goes over with 1 watt, that is the same as 1 joule. And the amount of we have needed as gasoline, or the potential difference we have lost in our ampere to go over to the other side, is 1 watt. That's the definition of 1 watt. Both these statements defining a volt, although differently worded, mean exactly the same thing. They make it clear that the power of the rate of conversion of energy associated with the current depends directly on the potential difference associated with it. Expressing this fact mathematically, volts multiplied by amperes equals watts. Example: a main supply applies of 250 volts to an electric fire, and a current of 4 amperes flows through the fire. What is the power consumption and how much energy required to the unit? Let's come here just back to the next part. I think it's basically just the same as driving a car from one place to the other. The car has so much weight that has an influence on how much it's not so how. No, the weight is just defined. It has to weigh so much, because we cannot just say it can be a big truck, because it takes another amount of gasoline. We want to know what is the volt, and so we have to say no, it has to weigh a car of 1 ton. Drive it over. Guess how far? We cannot just say drive 100 kilometers, 100 meters. It has to be defined. So we're saying a car of 1 ton has to drive 1 meter far, and it also, how fast if a car drives faster, it needs more gasoline. So we're saying, no, you drive exactly a 1 ton car, 1 meter far, 1 second. And the amount of gasoline which has drawn, that is 1 watt. I think it's in basic that we're going to come back to the next part. We're going to come back so often as we understand it. Whatever. That was the electrical engineering part. If you were here for electrical engineering, you can go directly to an expert of electrical engineering. If you have a short and pinch training, then you can participate in the short and pinch training 2 minutes. Which is too short. But if you participate in the short and pinch training, that is better at your own risk. Go to 7 stands and we do short circuits. Come back, up, front, and down. And backwards and front. Up, and down. And now long arms, strong fists, and go as far back as with the shoulders as you can. High up, front, and down. Back. Up, front, down, and again. Up, back, down, front, up, back, and down. And now, long arms, strong fists, bring your shoulders down and together. Turn the arms to the inside. Arms to the outside, shoulders down, together. Arms to the inside, shoulders down, together. Arms to the outside, shoulders down. And release. And arms to the sides, a bit in front, turn the arms in front, shoulders down, together. Arms back, shoulders up, down front. And in front, down and back, and together. Again back, hop back and front. And now a shrug, not a shrug, a stretching. One arm, no, that's a shrug. Arm up, that's good. And no down. And now stretching. One arm in front, pull the arm in. The other arm in front, pull the arm in. No, that was a very short shot. I thank you very much, and until next time.